This work of ours started with the question, how do we stop oblivious access schemes from leaking object links? And since then, it's led us to some unexpected and interesting results. So I'll be sharing those with you today. Our focus is on the cloud storage setting. For example, a hospital storing medical data on a cloud service. For example, Amazon S3. The data is stored as key-value pairs with a disease as the key and a list of patient records as the value. Even though this sensitive data is always kept encrypted on the cloud, the adversary, usually the untrusted cloud provider, can still learn about it by observing the client's access patterns across the encrypted keys. Knowing the real-life distribution of disease cases, the adversary can infer, for example, that the most frequently accessed key is flu. Then, when the client next accesses an encrypted value, the adversary can directly identify the plaintext key. This problem has been addressed by research on oblivious data access, and it's now a very mature field. Most works in this space hide access patterns by injecting fake key-value pairs into the store or fake accesses to keys, but they crucially ignore the lengths of stored values. Say we apply oblivious access to make the observed access frequencies uniform. The store is still vulnerable to length leakage attacks, where the adversary can observe the varying sizes of requests to and responses from the store, and then use these to identify access keys. The space of hiding both lengths and access patterns is still developing, with only a few prior solutions that we'll get to later. Characterizing the space and providing bounds on what performance is possible is the focus of our work. This brings us to our contributions. First, we introduce a new security model that considers both access pattern and length leakage. Second, we explore a new three-way trade-off that's opened up between security, bandwidth, and storage. Third, we prove performance lower bounds under our considered security settings. And fourth, we achieve these lower bounds using secure constructions. I'll cover each of these in the rest of the talk, starting with our first contribution, a new security model combining access pattern and length leakage. Recalling our setup, we assume a passive persistent adversary that can't inject queries of its own to the store, but can observe its encrypted contents and a transcript of encrypted client accesses. For baseline security, we must always hide the mapping of plain text to encrypted keys, and we formalize this requirement as ROR CDLA in our paper. This basically means that all values in the encrypted store are the same size, and the access distribution over these encrypted keys is uniform. Even while fulfilling this requirement, the adversary can still observe metrics like bandwidth footprint, which is the number of bytes fetched per query, storage footprint, the number of bytes needed to store all values, and the number of keys in the encrypted store. These metrics can depend on underlying distributions of the plain text data, which we capture in the following leakage profiles: the largest value size, the value sizes before encryption, the access distribution, or a combination of the two. Given this leakage, the adversary still cannot map plain text to encrypted keys, since it only sees encrypted values of the same size with a uniform access distribution. So to see what different leakages imply, let's look at two prior solutions with opposing designs. One design is based on prior oblivious access mechanisms, and those assume same-sized input values. So then this design trivially pads each value to the largest size before storing and encryption and storage. The other design is based on size-locked indexes, which pack the entire database into one encrypted bin that's returned for every query. We say design 1 leaks that the largest value size is 5. And if we execute this scheme on a data set with a different largest value size, then the adversary can distinguish between these two executions. Design 2 leaks that the sum of value sizes is 10. And this allows the adversary to distinguish between data sets with different sums of value sizes. We see these solutions offer different leakage guarantees, But they also make trade-offs in bandwidth and storage footprint, which brings us to our second contribution of uncovering the trade-off space between security, bandwidth, and storage. We can say that design 1 has less leakage than design 2, since it only leaks the largest value size. Meanwhile, the sum of value sizes in the worst case leaks not only the largest value size, but also information about the rest of the value sizes. Design 1 also has a lower bandwidth footprint since it transfers less bytes per query compared to design 2, but it has a higher storage footprint as its padded value sizes add up to 15 compared to 10. These schemes cover different priorities in this trade-off. For example, if we're in a bandwidth-constrained environment, then we might prefer to use design 1. Our work generalizes this trade-offs to other solutions and leakage profiles, which we'll see next. We consider the following leakage profiles, which we chose as extremes in the space of leaking axis distribution and value sizes. We view the trade-off space with leakage on one axis and performance overheads on the other, where performance is defined as a scheme's bandwidth footprint given a fixed storage footprint. While we can parameterize this in other ways, we focus on bandwidth as it's usually the scarcer resource in the cloud. For our third contribution, we map each of these leakage profiles onto the space by finding the lower bound on the bandwidth achievable by any scheme given fixed storage. Our fourth contribution achieves these bounds with secure constructions, two of which we've already seen. Design 1 leaks the largest value size, and design 2 can be generalized as a bin packing solution that leaks all value sizes. We also have new constructions for the other two leakage profiles, but we'll not cover them here. If you're interested in learning more about them, please check out our paper. What we find here is the trivial padding solution is surprisingly optimal if you only want to leak the largest value size. But the performance bound it achieves is prohibitively high for most real data. Loosening these leakage requirements improves the lower bounds, as we can see from the gap between leaking the largest value size and the rest of the value sizes. As we go from a log y-axis to linear, we see that this performance gap is actually quite large in practice. Now let's see how this improvement is achieved by first looking at our construction based on design 1. Consider an example input with the axis distribution skewed towards keys with larger values. We use the prior Oblivious axis scheme pancake to hide this axis distribution. Given a fixed number of values in the encrypted store, it creates as many replicas of the popular keys as possible and divides axes across them. Then, to achieve a uniform axis distribution, it sends additional fate queries to the unpopular keys. Pancake doesn't hide length leakage, so the only step to make it ROR CDLA secure is to pad all values to the largest size. This resulting scheme, which we call padded pancake, actually achieves the bandwidth lower bound that we derive in our paper. Put simply, given a fixed storage footprint that is a multiple C of the largest value size S max, the minimum bandwidth footprint needed for ROR CDLA security is some multiple D of S max. D is a function of C and the number of plaintext keys N, and it becomes a constant with large N. This bound is expensive for data with a wide range of value sizes, since they all have to be padded to S max. For example, we see 30 times bandwidth overhead on 2 times storage overhead in our evaluation. Now let's see how bin packing reduces this bandwidth footprint given the same input. Instead of padding all values to the same size, the scheme can now bin pack the unpopular values together, which makes room for more replicas of the popular keys and reduces the volume of traffic sent to the unpopular keys. While the traffic volume now depends on the value sizes, the identities of individual keys are still hidden, preserving ROR CDLA. This scheme, which we call stuffed pancake, achieves the bandwidth bound for leaking value sizes, which is as follows. Given the same fixed storage, the bandwidth bound is now a smaller multiple D star of S max, and it can get even smaller depending on how packable the value sizes are. This gave us significant performance improvements, such as 30 times to 6 times bandwidth overhead. Now, for a quick note on evaluation, we used 2 real data sets containing tweets from 2010 and Wikipedia page contents. But this talk only shows numbers from the Twitter data set. As I've mentioned, leaking just the largest value size incurs high performance overheads of 30 times bandwidth, which motivates us leaking more information for practicality. In fact, we see that overheads decrease to 3 times bandwidth given the same amount of storage with our most permissive leakage profile. Many more details can be found in our paper, so please read on if you're interested. To conclude, here again are our contributions to the space, but there's much left to explore. Our work leaves open several questions for future research, like whether there are attacks that exploit the distributions in our leakage profiles, or analyzing other leakage profiles in this space, and adapting our framework to the ORAM setting, compression-based schemes, and more. This ends my talk, and I'm happy to take questions.